Hey everybody, Mr. Gajewski here, and today we're going to talk about solving special systems of linear equations. So let's jump right into it. Let's zoom in and take a look at these three graphs over here. So remember, a system of linear equations is two or more equations with two or more of the same variables. Each equation in a linear system can be represented by a straight line. So if we look at our first example, we have a red line and a blue line, and they meet at one point. That point is the solution to the system. So what can we say about these two lines? Well, these two lines have different slopes. So when we have two lines with different slopes, they will meet at one point. That one point will be our one solution. Let's take a look at this second example, the example in the middle. We have two lines that do not intersect. Remember, in order to have a solution, the lines must intersect. Because these lines do not intersect, we say no solution. Another name for lines that do not intersect would be parallel lines. So we can say in this second example that these two lines, the red and blue, are parallel lines. And what do we know about parallel lines? Well, they have the same slope, but different y-intercepts. So they're moving along the same direction, but along different tracks, per se. So same slope, different y-intercepts, we say no solution. And how can we tell by looking at the graph? The lines do not intersect. Then we'll take a look at the example all the way to the right. So this purple line is really two lines laid on top of each other. So we have a red line and a blue line. We mix them on top of each other. We get a purple line, one solid purple line. What does that mean? Infinitely many solutions. Remember, the solutions are the point where the two lines meet. These two lines meet at an infinite number of points. They are the same exact line. They are represented by the same equation. So how can we tell by looking at the equation whether or not we have infinitely many solutions? Well, they have the same slope and the same y-intercepts. When you see two overlapping lines or two equations with the same slope and same y-intercept, we say infinitely many solutions. We can also find whether or not we have one solution, no solution, or infinitely many solutions algebraically. We've already done plenty of examples using one solution. Now we're going to see how can we find algebraically no solution or infinitely many solutions. So I'm going to go ahead and I'm going to take a look at my first example here. Now there's a couple different ways I can solve this. I can compare the slopes and the y-intercepts and then look back at my chart to see whether or not I have one, no solutions, or infinitely many solutions. I can make a graph, compare the graphs to my chart over to the left, or I can solve this system algebraically using either substitution or elimination. Let's go ahead and let's make a graph here. So this first line, I'll use blue, we have a slope of 3. Remember, the slope is the coefficient of x when an equation is written in slope-intercept form. And then the y-intercept, the b value of slope-intercept form, is positive 1. So I'm going to plot my point at positive 1. Then I'll plot another point up 3 over 1. So the slope has a rise of 3 and a run of 1. All right, I'm going to go ahead and draw a line between the two. I should really extend that. There's my first line. Let's go ahead and in red, we're going to make our second line. Slope of 3 with a y-intercept of -3. So this one's going to cross at -3. And again, our slope is our rise over our run. It's going to go up 3 over 1. I can actually do that a couple times to give myself a better idea of where this line is going to go. Let's go ahead and draw a straight line. So what do I notice looking at this graph? Well, these lines do not intersect. If I take a look back at my chart, well, lines that do not intersect, parallel lines, those have no solution. So this system up here at the top of number 1, we say has no solution. Now we don't quite have to make a graph. We can also just compare the slopes and the intercepts. So again, we have same slopes. They both have a slope of 3, but different intercepts. So same slopes, different y-intercepts. Again, no solution. But we can also solve this algebraically. So if I rewrite this system down here in the bottom right, y equals 3x plus 1, and y equals 3x minus 3, well, my two methods algebraically for solving systems are substitution and elimination. Now this is set up to solve with either method. We can substitute here, we can eliminate here. Either one is going to work really, really well. I'm going to go ahead and I'm going to use substitution here. So I'm going to take this 3x minus 3, and I'm going to substitute it for y in the first equation. What's that going to give me? Well, that'll give me, instead of y, I have 3x minus 3 equal to 3x plus 1. Let's go ahead and let's collect our variables to one side. So I'm going to go ahead and I'm going to subtract 3x from both sides. And that'll leave me with -3 equals 1. So we have no variables and a false statement because -3 does not equal 1. So what can we say about a system of equations where we get a false statement? Well, very similar to solving one equation with one variable. When we get a false statement, we can say no solution. So let's go ahead and let's take a look at another example. So here's another system I have. 4x plus 8y equals 36, and 12x plus 24y equals 108. Now again, I could graph. That might be a little difficult because I'm going to have a hard time. Well, I really can't graph using intercepts. I can't, well, I could, and I really can't graph using or rewriting this in slope-intercept form. I could use substitution, but then I'd have to solve for a variable. I don't really like any of these variables to solve for. There's going to be a lot of distributing. So I am actually going to use elimination. I have my x's lined up, my y's lined up, my constants lined up. The only thing is I don't have matching coefficients. So I'm going to have to multiply one of these equations before I eliminate. So I need to think to myself, what's a common multiple of 4 and 12 or a common multiple of 8 and 24? Well, just looking at my x's there, well, a common multiple of 4 and 12 would be 12. And that works out real nice because I don't have to multiply the second equation at all. We already have a 12x. And I only have to multiply the top equation by 3. So let's go ahead and let's do that. So we're going to multiply both sides of this top equation by 3. And then I'll rewrite that top equation underneath. So that'll give me 12x plus 24y equals 108. So now you might notice something a little funny here. I have a system of equations where both equations are exactly the same. Now, just to be safe here, let's go ahead and let's eliminate and see what happens. So I could subtract these, or I could multiply by a -1, which would just change all the signs. So let's go ahead and let's change the signs. So in this second equation, this negative 12x will be, or excuse me, this 12x will become negative 12x plus a negative 24, and then positive 108 will become negative 108. Now I'm going to go ahead and I'm going to combine the two equations. Well, 12x plus a negative 12x is 0. 24y plus a negative 24y gives me 0. So I have 0 on the left-hand side of my equation. And then, well, 108 minus 108 is going to give me 0. So now I have no variables and a true statement, because 0 does equal 0. I just don't have any variables here. Well, what does that mean? Well, similar to solving an equation. What happens when I have no variables and a true statement? I can say that there are infinitely many solutions. So again, if I think about this, if I were to graph these two lines, because they're identical, their graphs would be identical. And when their graphs are identical, just like our chart up above, they're going to overlap. So there's going to be an infinite number of points that we could plug into this system that are going to give us a true statement. Now that doesn't mean I can just plug in any numbers. It would have to be a number that is on the lines. So this is not to be confused with all real numbers. So there's an example of infinitely many solutions. So just to recap here, looking at graphs, if they intersect, they have one solution. Parallel lines have no solution. Lines that coincide with each other have infinitely many solutions. Equations with different slopes have one solution. Equations with the same slope and different y-intercepts have no solution. Equations that have the same slope and the same y-intercept have infinitely many solutions. If we solve algebraically and we end up with a false statement and no variables, we say that there is no solution. If we solve algebraically using substitution or elimination and we end up with a true statement, then we can say that we have infinitely many solutions. So that is it for solving special systems of linear equations. I hope that helps. If you have any questions, please let me know. And I will see you next time.